हेलो। हेलो अनिकेत।
हेलो। हेलो।
हाँ। हेलो।
हेलो मोली।
हाँ भाई, पता है कैसा है तू?
बढ़िया। और
मस्त। तो कहाँ है अभी, दिल्ली में ही?
अभी तो पता चला एग्जाम ऑनलाइन होंगे ना।
ओह, मुझे नहीं पता एक्चुअली। कब पता चला?
ग्रुप चेक कर।
ओह, एक्चुअली सुबह से मतलब मेरा तबीयत, मतलब कल रात से मेरा तबीयत बहुत खराब है, इसलिए सुबह क्लास की अटेंड नहीं कर पाया।
नहीं नहीं, तू बस ग्रुप चेक कर, क्लास में कुछ नहीं हुआ। जस्ट चेक द व्हाट्सएप ग्रुप, मृणाल है सेंट एन इंटरेस्टिंग स्क्रीनशॉट।
ओह, अच्छा अच्छा अच्छा, रुक मैं देखता हूँ।
हम्म।
मतलब ये कॉन्फर्म है कि ऑनलाइन ही होगा एग्जाम?
नो, जस्ट एक बार वो स्क्रीनशॉट पे जो
अच्छा
लिखा है उसके हिसाब से पता चलेगा, बट आई एम नॉट श्योर क्योंकि हम सबको तो नहीं बताया।
अच्छा अच्छा अच्छा,
ओनली
एक मिनट। हम्म। उधर सर्दी कैसा है?
सर्दी मतलब आई गेस 10 डिग्रीज।
बाप रे।
एग्जाम्स तो अब ऑनलाइन ही होंगे ना।
इसका वो कंफर्मेशन आया है क्या?
ये स्क्रीनशॉट भेजा ना मैंने।
वो
नो
मृणाल ने कुछ
ऑफलाइन। आई डोंट नो इफ इट काउंट्स एज अ कंफर्मेशन, बट वो जो मेल भेजा है ना उसने पर्सनली,
अच्छा, ओके ओके, हाँ मृणाल ने एक मेल भेजा था तो हाँ, तो उसका क्या रिप्लाई आया था?
कि देयर विल बी नो ऑफलाइन फाइनल एग्जामिनेशंस फॉर बीस्टेट थर्ड ईयर दिस सेमेस्टर फ्रॉम
ओके
देवाशीष sir.
ओके, चलो ठीक है।
So that sounds like a confirmation.
दैट अगर सर डीन सर ने किया था तो हाँ, फाइनली समझे।
Good afternoon, sir.
Yeah, good afternoon. Let us start in just
आफ्टरनून सर।
a couple of minutes, okay? Yeah.
Okay, sir.
Yeah, hello.
Yes, sir.
Yeah, so we can start today. Yeah, so before I start, so any questions about whatever was done in the last class? Or anything on that direction? Okay, so so let's see where we were. We were. Kind of left you guys with the question of how to have a share my screen first. Yeah, how to find a matching, right? So question was that, okay, if I have a matching, I mean, I've given a graph G and I want to find a matching. What is the matching? Matching M is the subset of the H set such that for all vertex V, right? For all vertex V, there exists at most one edge E in M such that E intercept, I mean, V is the part of the edge, right? So this is the matching. And the question is that we want to find the, or if I'm not saying the, maybe a maximum matching. Not that I'm not asking you to find a maximal matching. Maximal matching is very easy to find. Maximal matching, how can you find a maximal matching? Can you guys say quickly?
So some greedy algorithm.
Just a greedy algorithm will do, right? You just keep on picking it up and till you time you can. At some point of time, you cannot take an edge, right? So basically you take an edge, remove all its adjacent edges. Then pick another edge from the remaining graph and remove all that adjacent edges and keep on doing till the graph is empty. And that will give you a maximal matching. And of course, the time complexity will be linear. Okay. So by the way, I nowadays, as you can see, I sometimes don't go details into the time complexity analysis because I am expecting that you guys are able to understand some of this basic stuff that, okay, this is linear or so on. If you are not, if you want me to kind of explain why this such a thing is linear or something like that, yeah, please feel free to ask me. Okay. Now so how can you find a maximum matching? And we saw that this maximum matching is an LP or can be represented as an LP. Not LP, sorry. If I could have represented it as an LP, I would have been done as an ILP. Right. So now that we have an ILP for that maximum matching, and the problem is that LP is in P, I know that, but ILP is not. ILP is NP complete. So as such, this doesn't help us to solve this problem. So how can we go about it? Yeah. So yeah, so tell me, any ideas? How can we go about this thing? How can you come up with an algorithm? Nobody has any idea? So let's see. So what is thing that we have seen so far? We have seen that network flows or maximum network flows This is in LP, right? Very good, done. Wonderful. So that means this is, I mean, this can be written as an, I mean, I said this is a bad notation. This can be written as LP, and since I know LP is in P, I can solve network flows in polytime. Now, of course, the problem is that the network flows need not give you a, so even if, so what is a network flow? So I have this thing. Okay, so let's say I make all of them 1. And what is the maximum flow that you can send from S to T? And the answer is 1, and this might be like send 1 unit here, half unit here, half unit here, half unit here, half unit here, and 1 unit here. And this is a flow that sends 1 unit from S to T. The problem is that this is not giving us a integer solution, right? So even if, yeah, sorry. So even if when the graph has edge weights integers, even then we cannot guarantee you that it will have a integer solution. Okay, but that is where we saw that if I have this graph and the weights are from the edge set to say natural numbers, not just reals. Okay, then let's positive natural numbers. Actually, yeah, whatever. Then maximum flow. Okay, what can we say? Of course, maximum flow can be solved in polynomial time. That is by default, because that is any network flow can be written as a LP, and you can have a polytime.
Max flow is also an integer. Then
max flow is also an integer. Then max flow is also, or rather, I would say not say that. Okay, so let me write it here. Okay, then there exists a integral max flow. I'm not saying that all flows are integrals, but there exists an integral max flow, right? For example, here this is a flow, but that is not an integral flow. But all I can say is that, see, you have given me this thing, but you could have sent 1 unit here, 1 unit here, 1 unit here, 1 unit here. That would also have achieved the same amount of flow, and that would have been an integral max flow, right? So if I give you this one, and what we also saw is that Ford-Fulkerson
so can you give a proof of that statement?
Which one? This
So
statement?
like yes, so I understand why the value of the maximum flow is an integer. I don't understand like if it is necessary that we can always find a all in.
Yes, so this is exactly the proof of the correctness of the algorithm that I gave last class, the Ford-Fulkerson algorithm.
Okay, it follows from the proof. Okay.
Yes, the Ford-Fulkerson algorithm is finding a max flow, right? And what does it do? It at any point of time finds a path from S to T, tries to push as much amount it can pass through that. Basically, it looks at the weight of the minimum weight among the path and pushes that much amount through that path, right? But since all the edge weights are integers, that means I am updating. So I'm adding a path, but all the edge weights are, or I'm pushing a flow, an integral flow from S to T. So every time the Ford-Fulkerson algorithm updates the flow by adding a path through which another integer amount is being passed. So at the end, therefore, you are slowly getting integer flows only. So Ford-Fulkerson algorithm always maintain integral paths. Is this clear?
Yes, sir, it's fine. Yes, sir.
Yes, sir.
Okay. Yeah. So this proof of this thing actually follows from fourth Fulkerson. Okay. And this is good. So that means I can actually find an integral flow. So in other words, what happens? If I can, therefore, so if I can write or maybe write is a good option, or write or not write, okay? If I can view maximum matching as a network flow or max flow on a graph with max flow in a graph with integer weights, then we are done, right? So if I can write the max flow and the integer weights, then we are done. Everybody with me?
Yes, sir.
Yes, sir.
Okay. So now let me give you another couple of minutes. Okay. Why don't you guys just try to see how can you find the how can you write the max flow or maximum edge weight? Okay. Okay, maybe this is not actually that easy. Okay, so think about, let's start with this one. Okay, what happens? Consider the maximum matching in a bipartite graph. Can you write this one? Can you now, using whatever we have seen till now, can you solve it? How would you write a network flow? So let me give you all a couple of minutes. Okay, it's pretty easy. So just all of you do it on yourself, and then I will ask. Okay, if I have a bipartite graph, how will you find the maximum matching in a bipartite graph? And you have to also, why don't you think about the fourth Fulkerson algorithm and try to understand, tell me what is the time complexity of that algorithm overall. Okay. Ritam. Hello. Ritam, are you there? Maybe yeah, I cannot hear you. But I cannot understand. You wrote a question to me. I did not understand. Is it a question or you are making a statement? So for now, let's not worry about the weights. Okay. Sorry, did I make a mistake? See, I am not saying here. I am not. So I want to find a maximum matching in a bipartite graph. So there is no weight. Okay. So that means I just have a graph. That's it. I'm not saying to find the maximum matching, not in the sense of sum of the edge weights. So I want the matching is a subset of the edge set. The maximum matching is basically trying to maximize maximum matching. You want to maximize the number of edges in this set M. Okay.
Sir, I
Yeah.
think I have a solution.
Sorry.
Sir, what if, sir, can I propose a solution?
Just one second. Just one second. So before you propose a solution, maybe can I just ask any other doubts about it? So I mean, I think there might be some miscommunication about
Sir,
this
we should
problem.
think in terms of network flows, right?
You can write it in terms of network flow. So you can of course choose the edge weights of that network flow. That's fine. Okay.
Sir, but what is the source and the sink? I mean, I could
That's
not.
up to you. You decide. You can create the network flow. You have a graph, a bipartite graph. So you can think of the bipartite graph as so the V is actually. So maybe you can think of the graph to be not GUV but GUVE, right? So U, V, and all the edges are in between. What's the source and sink that you think? This one I want all of you to think actually very carefully, okay? It is not hard, but I have been giving you a graph. There is no edge weights. There is no source or sink, okay? I want to find the maximum matching in the graph. Maximum matching is maximum number of edges. Now, I am giving you a hint. Hint is reduce it to network flows. How do you reduce it to network flows? So you have to create a network flow. You have to create a weighted graph with the source and the sink, such that the maximum. So I give you a graph G, right? This is the graph in which I want to find a matching. You want to create another graph G prime and a weight. So G prime has some, say, V prime comma E prime, and a weight that is from E prime to natural numbers, such that a matching here should correspond to a flow here. Okay, the flow in G. How do you do it? Okay, so that's the reduction that you want to create. Yeah.
So is it because of the minimum cut thing that we get? So
This is not because of a property. You have to construct this G prime, right? I'm not
Yeah,
saying so. This is not a proof that I'm asking. I'm asking you to solve to give me an algorithm, right? Which basically means that I will give you the G. You have to give me the G prime.
Sir?
Yeah.
So for G prime, what we can do is take a source vertex.
Yes,
a dummy
yes,
vertex.
you got it. Just one second. Let your friends,
Yes.
friends think and do it. Okay.
yes, so for bipartite, I guess we can do something.
Yeah, bipartite only. Let's do it for bipartite for now. Yeah.
Yes, sir.
Once if you're done, okay, why don't you try to tell me or try to find out how much will the time complexity of it, of the algorithm. And particularly if you think you are done, why don't you please send me a chat or something that I am done or something. This is something I really want all of you to get it. So this is very simple. Okay, but it's very important because you are reducing one problem to the another. Okay, I have got 2 persons have told that they have got it.
Sir,
Yeah.
I think I understood it, but I'm not sure. So, sir, if we take a source and so we have a two-partite thing in the bipartite graph,
Right.
and we
Right.
try to connect the source with one partite and the sink with the other partite, and try to find the. So how are we assigning the weights then? Because the graph is not weighted.
The graph is not weighted, so you can put weights whatever you want.
So, but that will have a say in the solution. So if I cannot
Yeah,
put,
you have to choose the weights correctly.
so if I'm choosing, so if I assign weight C to every edge,
Hmm. You can weight C to every weight, but what is C? Some C?
some C, yeah, equal C.
And what about the sources and the sink? I mean, this is I'm finding this thing the most confusing.
Okay. So here is the graph.
So
Okay.
equal C won't work, I think. So using the example above that, hello.
Yeah, yeah.
So just the example here keeps that one diamond and
Yes.
so if
Right.
you,
This one?
yes sir, using this the C must be what?
Hold on. Don't think in this. C must be 1. Yeah, you're correct. So let me go. I think many of you are actually struggling with various concepts here. Okay. So this is the graph, right? Right?
Yes.
And I want to find the maximum edge. What maximum? What is that called?
Right.
Matching, right? So maximum matching was something like it will look like something like this, right? This one. Okay. Fine. That means what is important is that this is getting matched to here, 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 right? And okay, maybe I can draw another vertex here. Okay, so maybe there is some vertex over here. I don't know what is it. No, that's not good. Say like this. Okay, so this is maximum or any matching is of this form, right? Any matching is something of this form. I don't know maximum or not maximum. What does it mean? That this vertex, can I map it to something else? Can I map it to here? No, correct? Because this has already been mapped to here. Similarly, this has been mapped to here. I cannot map it to here, and so on. So every vertex that is mapped can be mapped to exactly one thing, right? So that is the intuition. So let's see, how can I give you a new graph? I draw a new set, sink here. It's I have to create a graph, right? What happens if I just draw edges to all of them? I'm trying to push water through. And I draw a new C over here and I attach all the edges over here. Now what happens here? I just say put directions. Now let's see what happens. So thing is that I want to push water from S to T. The idea is that if I can push, if I am mapping this to this, why not I push some water through this? If I'm mapping this to this, why not I map water through this? If I'm mapping this to this, why not I push water through this? And so on, all right? So in some sense, you can see that if there exists a matching of size T, then I should have T different disjoint paths from S to T.
Yes.
Excellent. I'm not giving you weights yet. Okay, so weights has to come up slowly. Okay. Now, but there can be other paths also possibly, right? For example, what happens to this path? Say, I can send weights from here to here and then here. This is also a path, right? Now this one I don't want to allow it. But if I allow it, then see this particular vertex is getting mapped to kind of this and this twice. Right? I want to stop that. So how can you do it?
Sir, since hello,
Yeah,
sir, can I try?
yeah, go ahead.
Since this will be an integral flow,
Yes.
so it will not divide the into different weights. Suppose if I need to push 2 units of water, then I will not divide them and one to each. So I need to do in such a way so as to it will only be forced to go through them. So it
Yes,
will be
how will you
1
force?
unit.
How
Sir,
will you force?
So we will put 1 unit. The capacity will be 1 unit in each of them.
Capacity you are putting is 1 unit where? Here.
Yes, sir. In all, yes. Sir.
You put 1 unit here and 1 unit here. What is happening? That I am want to push at most 1 unit through this point. 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 And in other words, from here, at most 1 unit can go out. From here also, at most 1 unit can go out, and so on. Now, because it's an integral flow, that's what I'm trying to get. So if I push 1 unit from here, it has to come out as 1 unit only, and then go like this, right? If I push 1 unit from here, and this thing comes, then if this goes here, then this cannot come. That cannot be, because this one has the weight 1, right? So by doing so, and now if I even keep this edge weights here, even infinity for that matter, I have no problem of whatever is what we are doing. So any natural number you put.
Hello,
Yeah, hello.
can anyone? Hear me? Hello, yeah, yes. So, is it necessarily one it, but I mean, any equal weight will it suffice? I
Will
mean,
it
say
suffice? Tell me,
I
will it
give
suffice?
2.
Okay, what happens if we have 2? What happens if I have 2 here?
That can be broken up in 1 and 1. So
Exactly. If I have 2, say I have 2 over here, I can set 1 unit from here and 1 unit from here. Right? 2, 1, 1, 1, 1. So then I am going to map this to this, or this to this. How can that be a matching?
Sure, but if we do the fourth Fulkerson, then it will be the same, right? Because
No,
we will
no,
always
no.
have paths of 2.
No, that's not true. Okay, you are saying that if you have all of them 2, then it will have parts of 2 if all of them are multiple of 2. Okay, you are right. If you have all of them are multiples of 2, then you can. Okay, I mean, okay,
Yes,
you are
yes.
right. I mean, but then you
That
cannot use.
there exists
Sorry,
that, yeah.
sorry.
So my question was, instead of those infinity,
Okay, if you have
I-
all 2, then how can you prove it? Tell me.
I give them.
No, Abhijit, I cannot hear you.
Can
Abhijit, I cannot hear you.
you hear me?
No, I cannot. Okay, so if you have all of them are 2, then also, as somebody pointed out, it will work.
I'll hello.
Abhijit, we cannot hear you. So it will work, but
I'll give.
Abhijit, we cannot hear you. Yeah.
Hello.
Yeah.
I think there's some kind of lag.
Can you hear us now?
Yes, I can hear you. I think some kind of lag in my side in microphone. Okay, I'll send it in chat if I have some problem. Okay.
Sure, yeah. No, see, if you have all of them true, then it will be true. But then what you would end up needing to prove, which is true, that in the fourth Fulkerson, if every edge weights is a multiple of 2, then the algorithm will also end up producing a max flow where every edge, every flow value is a multiple of 2. Okay. I mean, which basically means the same thing, because if you have everything is a multiple of 2, then you can divide by 2 and just have all of them as weight 1 kind of stuff. But if you don't use the extra condition, but just have using whatever I have just proved, that fourth Fulkerson gives you an integral solution, then what you need is you cannot put 2 over here. You cannot put all of them 2 over here. Technically, there can be a problem, because what can happen is that, I mean, you have a 2 here, 2 here, 1 unit goes here, 1 unit goes here. I mean, like that, it can be a bit jumbled up. I mean, maybe I have not able to explain you properly. What happens to this one? Okay, so all of them are say 2. You have to tell me why doesn't a fourth Fulkerson ends up sending 2 unit here, 2 unit here, 1 unit here, 1 unit here, 1 unit here, 1 unit here, and again 2 unit here, 2 unit here. So this is the integral flow, right?
Yes,
But this is kind of not what we were wanting, right? This is kind of exactly this half-half kind of stuff. But yes, fourth Fulkerson will not produce this. Fourth Fulkerson will end up will not, I mean, will send 2 in all of the place.
So this follows from the closure of even numbers
Yes, exactly.
under addition.
Exactly. Yeah. Yeah. But for all of you, is this clear that in this graph, okay, if so this is G prime, okay, so if G, so I will not say if, okay, so G has a matching of size K if and only if G prime has a flow or integral flow of size K. Is this clear? Chandramouli and Jyotish, who of you are asking about this just start state and end state?
I was asking, sir.
Yes. So now is it clear, this thing?
Yes.
Yeah. So see, this is exactly where it happens. You have been given one problem, right? That problem might not have what say start state, end state, weight. It might not be even a graph problem. But when we are trying to use or reduce it to something else, say the flow problem, then I have to create that flow network. So here, because it was a graph, then possibly you got confused. But this is a graph. You should kind of forget this graph. So this is a graph. Using that, you construct another graph. Now, in this graph, this has to be a network. So this is not a graph. In fact, this should be a network. So given a graph, construct a network. Okay, such that this is satisfied.
So for this statement, the forward implication is trivial. To
Yes.
prove the reverse,
Yes. Tell me how the reverse is not. How do you prove the reverse?
so we can say that if there exists an integral flow of size k,
If there's an integral flow of size K, yes.
that means k of the edges from S to the U set must
So
be
there has to be K distinct paths, disjoint paths from S to T, right?
right.
Because since every vertex here on the left hand side has in degree weight 1, I mean the amount of, and each of, so there no two paths can use this
Sir, hello.
this vertex. Similarly, no two paths can use this vertex, right?
Yes, sir. Yeah, right. So since all the paths have no edges in common,
Yes.
then that means that no vertex is being shared, and
Right.
hence the inter-partition edges are all independent of each other.
Right. Yeah. Somebody was saying something. Somebody had some question. Was it?
Sir,
Yeah.
sir, won't this be a maximum matching and maximum flow?
It will be. I mean, I'm just saying that I'm just, so whatever is written is that if the graph has a matching, then the graph has a flow, right?
Yes.
So if I want to find a maximum matching, how will I do it? I will find the maximum flow.
Yes, sir.
Chandramouli, is it clear?
Yes.
Yeah.
Yes. Yes.
So all I have to do is that create this graph G prime and find a maximum flow there. Okay. Now, how much time will it take?
So
much-
there are
Yeah.
mod v number of paths maximum. I mean order of mod v,
Hmm.
and to generate each path it takes order of mod v plus mod e times. So maybe mod v times mod e, and here also the number of edges is also bounded, but it's v squared. So order of mod v times mod e, I think.
It's the order of mod v times mod u. Okay, so I mean, if you just do this kind of Ford-Fulkerson, what is Ford-Fulkerson does? It finds a path from S to T, right? Finding a path from S to T takes order v plus e, right? Once it takes a path from S to T, it kind of uses it to make one flow through that path, creates the backward paths, I mean back of the reverse edges, right? Get the reduced graph G of f, and in that new graph again, which are the same set of edges and same set of vertices, right? It finds another path and again it updates it. Now, how many times it updates it? Every time the edge weights is going up by at least one. So the flow quantity is going up by at least one, and the maximum flow that can happen here is at most v, right? Because it's a graph cannot have more than v number of matching, right? Or v by 2 or something. So this into v, which is basically order of e times v. Is this clear?
Yes, sir.
Yes.
Yes, sir.
So using Ford-Fulkerson technique or method, you can find a matching in order e times v. Now, okay, see, then we have to kind of ask, can you do better? Okay, now actually you can do better, and this algorithm is very interesting. I don't know whether I'll be able to give the whole algorithm or not, but before I give it to you, okay, let me ask you one thing. Say I have a graph G, okay. Oh, first of all, I have not done another thing. Okay, so this is the homework. What about non-bipartite graphs? Meaning maximum matching in general graphs. Okay, I want you guys to go back and think about this particular problem. How do you find the maximum matching in a general graph? We just did it for bipartite graphs, right? In the general graph, can you use the similar technique? Okay, this is more trickier, I must say, but you will have fun trying to solve it. But okay, so let me start with this one. Okay, so let's say I have given you a graph G. Okay, and somebody has given you a matching M. It's M is a matching. Okay, I am not writing in what does the matching means. But M prime is bigger than the size of M prime is bigger than M, and M prime is also matching. Okay, so we can also think of it this to be a maximal. Okay, if I mean it is a matching, but may not be the maximum matching, but it's at least maximal. Okay, M is a maximal matching, and M prime is this is a bigger match. How will M and M prime look like? How will M and M prime look like? So say for that matter, okay, it's weird. How did it become bigger suddenly?
Sir,
Yeah,
so in the last semester,
yeah.
we've done some analysis on what their intersection looks like and what their difference looks like.
Right. What
Something.
does it look like?
Just a second.
How does this intersection and the union and such things look like? Think of it as a graph. Okay, just look at a graph. Okay. So say this is a okay. Say I have a graph. This is my matching. Okay, this is my M. Is this maximum? Is this maximum?
No, sir.
Okay, no. Can you tell me why?
Because there exists some other matching.
Okay,
which
what
are
is the
bigger.
matching?
So you can connect 1 and 2 is fine. You can connect 6 and 7, then 8 and 9, 3, 5, and 10, 11.
Okay. Can you see what's the pattern happening here? What you just told?
So
So the
there is
chain
some-
is
Yeah, Ankit, go ahead.
So there was this concept of an augmenting path.
Right. I think this is exactly what the other friend also told. Okay. So look at
Right.
this graph, this path. Look at this path. What is this path? This path has alternating matching edges and non-matching edges. Okay.
Yes, sir.
So if I give you another graph, say if I use it green, say this one, okay. So this can be a matching edge, okay. It can also have something else also, right? Say it can have this thing. Sorry, I made a mistake. Right. So here what happened was that here also was a path. Consider this path. This path also had exactly the opposite.
Yes.
Meaning I have given you two things, M and M prime, right? If I look at this M union M prime, then what happens? If you look at it, it corresponds to this following thing. Or if I use M, maybe this is not a good idea to write M.
Sir, M is what and M prime is what?
M prime is a both of them are matching.
Oh, okay. Yes, sir. Yes.
Okay, M is a matching, M prime is a matching. Okay. Now I'm asking M disjoint union M prime. How does it look like? It can have a collection of these following two things. One of them will be
So disjoint union meaning we're going to exclude the elements which are in common.
so this means that I will exclude the ones that are in common.
Okay.
I mean, this is this XOR sign which comes from the F2 operations.
Yes, sir.
Okay, if both of them are one, then it becomes zero kind of stuff, right? So either you will have this kind of stuff, three kind of stuff will be there, which is a cycle, or you can have this kind of stuff, or you can have this kind of stuff. So all of them are collection of alternating paths or alternating cycles.
So why must this be true? Because every vertex is
Every
Cycle.
vertex will have at most two edges, right? Okay.
so, but what other structure could it have if it wasn't a matching?
No, it could have anything. What do you mean?
So you're saying that there can't be any branches to these kind of
They
things?
cannot be branches to anything.
Okay. Right.
Two greens cannot be next to each other. Okay, what I've used here is that M and M prime are two maximal matchings.
Sir, have we used that?
Yes.
So where do we use the maximality?
What do we use the maximality?
Oh, because we don't have red green red kind of a thing.
Have we used maximality? No, we don't need maximality. You're right. We don't need maximality. We just need matching.
So, but we did use the fact that M is greater than M dash.
No, I'm not used it anywhere. No, I'm just saying that give me any two matchings, then then this is how their disjoint union will look like.
So, but then we have to include the case where there are more number of reds than green in
No,
M.
that can also be happening. You're completely right.
Okay.
Yeah. Then the other thing that can also happen. Okay. I mean, I kind of added. I thought about the same thing. Yeah. Right. So They are alternate paths. All of them are alternating paths. Right?
Yes.
Now, if I so you have so this is something, I mean, a theorem, lemma, I am leaving it to you guys to go and prove it. Okay. If M is a matching, M prime is a matching, then M disjoint union is a collection of this kind of structures. Okay. Therefore, say if M is a maximum matching, say M is the maximum matching, which of this, okay, and M prime, okay, maybe I will use the grade. M prime is not a maximum matching. Then which of these structures can there be? Can you just tell me? So I will
The
put
first three that you're doing.
1, 2, 3, 4. Yeah. So can I have the fourth structure? Is it possible that I have a fourth structure?
No, sir, because we can just reverse green and red.
Oh, by the way, by when I mean structures, I mean these are the disjoint components. By the way. Okay, so these are the disjoint components. Looks like this. Okay. So if I have some structure like this, then what I can do is that I can add these two red things to M, remove a green edge from M, and that will still be a matching. Why? See, because the fact that this is max, this is a connected component. Okay, this is a component, which means that this is not connected to anything, right? In the matching M, this is also not connected to anything in the matching M, neither of them. Okay, in matching M, none of the blue edges exist, so they are disjoint. So this one was connected to here, that was fine. So now I can just add this edge and this edge and remove this edge, and this will also be a matching, though matching properties will not be violated, which means the matching M, therefore I can increase it, which is not possible because I assume that M is a maximum matching. So this is not possible. Okay, this structure is not possible. Okay. So in M and M prime, this structure can be there, this structure can be there, or this structure can be there, right?
Yes, sir.
Now, which of the structure has to be there? Which of the structures has to be there? In the
Three
DI?
has to be there.
3 has to be there. Why?
Because otherwise, if it was only 1 and 2, then they would have the same number of.
Yes, in the 1 and 2, the number of red edges is same as the number of green edges. So if it was only 1 and 2, then the number of red edges and number of green edges are same. So M would have been same as M prime. So 3 has to be there. Such an edge, okay. So we can also say that 3 or an edge like this, where the reds are in the middle and the greens are on the side, has to be there, right? So that means, so this is what is called, okay, or so if I give you a graph, so if I have M prime, and from that I want to somehow reach M, the idea is to find such a edge, right? So this kind of edges is what is called an augmenting path. What is an augmenting path? Let me define you properly. Okay. So
So this
given
would
a,
be augmenting path for the red
yes,
matching, right?
I'm doing that. Yeah. So if I give you a matching M or M prime in edge, an augmenting path for M prime, what is it? It is a path of the form V1, V2 till Vk, where crucially the first two things are there. V1 and Vk are not matched. Note that in this setting, in this graph, if you look at the red edges, then these two are not matched. These two vertices are kind of lonely, freely going around. They had no pair. So similarly, the first and the last thing has to be not matched. And what happens? The path is alternating between matched edges and non-matched edges. So is this thing clear? This idea?
Yes.
What about the rest of you guys?
Yes.
Yes, sir, it's clear.
Right? So importantly, if I give you a matching and if it is not maximum, there has to be an augmenting path. Right? And if you find the augmenting path, then I can increase the number of matching by 1. Okay. So an algorithm, another way of solving this matching problem is, here is the algorithm. Okay. Start with the maximal matching. I mean, it doesn't matter what matching is it. This is just a some matching. Even empty matching is also good enough, actually speaking. Then matching M. While there exists a augmenting path, P of M in G, what do? I kind of say that I just take this thing, M equals to M plus P. M equals to M plus P. So M plus P is what? I will take all the matchings, and for this path, I will just take the other ones, not the matched ones. And that's it. So that would give us a match algorithm for finding a maximum matching in a graph. Right?
So P
Yeah.
is all the edges are
all
one.
the edges in that path.
All the edges in this path are like a 1, right? And then we're using this XOR function. Okay.
Yeah. Okay. Now, are you guys convinced that this is an algorithm, right algorithm for finding a maximum matching?
Yes, sir. Because we've characterized maximum matching as something which has no augmenting path, right? So as soon as we reach that point, we would have reached a maximum matching.
Exactly. We have not characterized maximum matching like that, but we have proved that maximum matching, I mean, non-maximum matching has an augmenting path. Right. And we have proved it using pictures. But so what is the time complexity of this algorithm?
So it depends on how long it takes for us to find an augmenting path.
Good. So this is where your homework is, okay? Design an algorithm to find an augmenting path. Well, of a matching. I want you to go back and do it. Okay. Now, okay. So let me tell you, I am not going to give it to you completely. Okay. But using this idea and a slightly modification of this idea, which is very beautiful, and maybe I can come back a bit later on after you guys have thought about this problem a bit more. Okay. That there is an algorithm by Hopcroft-Karp. Of course, I'm letting you go and check it out in the internet if you are really interested in that, which will manage to find the same technique. Okay, it will kind of use the same technique, same algorithm, slightly different. That's I let you guys think how different is it. Okay, and you can obtain a square root v times e size algorithm for finding matching.
Sir, this algorithm does what?
Which algorithm?
This Hopcroft-Karp.
Yes.
This Hopcroft-Karp algorithm. I mean, what does it do?
It does the same thing. Okay. So all about this now, it's everything is in the finding the augmenting path.
Right.
Okay. So it basically tries to find augmenting path in a clever way. Okay. So in fact, maybe I can write it a bit more. Okay. So maybe I can give you some ideas, slightly different ideas of that. So what happens? Say I have a graph like this. Okay. So I have a matching like this. Okay. Maybe I should draw a graph. Okay. So here is my graph. Where is my matching? Can you increase the matching further? Hello, if I start with this matching, can you increase the matching by finding augmenting paths?
Yes, sir.
How?
So we can identify
3248 is an augmenting path, right?
Sorry.
This 3248 is an augmenting.
3248 is an augmenting path. Very good. Okay, very nice.
so 5, 6 is an augmenting path.
5, 6 is an augmenting path. Right. Good. Or maybe if I don't give you say 6, okay, let me not give you 6, okay, then whatever. So this is no
So
7.
5, 7.
So forget 7 is also not there. Then what?
So 1, 2, 4, 5.
See, this is an augmenting path, right? As some 3248, but at the same time, this is also an augmenting path.
Yes.
This is also an augmenting path, and this is also an augmenting path. And these two augmenting paths are disjoint, right? So if I call this one as P1 or P2 and this augmenting path as P1 and my matching as M, I can actually do M plus P1 plus P2. And at one shot, I can increase the size of the matching by 2. Correct?
Yes, sir.
So in some sense, what I'm saying is that you don't have to necessarily find a by augmenting path. You can find any collection of disjoint augmenting paths. Okay.
Yes, sir.
As long as there is an augmenting path, find a set of disjoint, I mean pairwise disjoint augmenting paths P1 to PT, and basically you just keep on adding them, right?
So, but there's no guarantee that in just this one step we will be able to achieve the
No, we will
maximum
not.
matching,
So we
right?
have to keep on doing it.
Okay.
Okay. So what Hopcroft Karp manages to do is that they are now able to find an algorithm to not only find an augmenting path, but find a number of augmenting paths in such a way that this whole loop cannot run for more than square root v number of steps. Okay, so I mean, if you want the homework for that, I can tell you. So this is the homework that I kind of gave you, right? That design an algorithm to find an augmenting path. You can actually come up with another design very similar to this, where you end up finding a collection of disjoint augmenting paths.
So we want to perhaps use some traversal algorithm to find all the,
Yes, you have to use some traversal algorithms. That's
which
completely
will
true.
be V plus C, right?
Yes, which will be V plus C. Okay. And using that trick, you can do this Hopcroft. If you can, so just by finding this, by doing this one, that what I told earlier, right? You take a path, add it, and so on and so forth. That algorithm should give you an order V times C algorithm. Something that we have got already from Fort Fulkerson. Okay, but you can also improve it to this.
Sure. So what if we were to just start from an edge, which was
Yes.
not part of the matching, and then just keep expanding until we reach
Yeah.
unsaturated vertices? Then just throw away these vertices from the graph and repeat the process.
Throwing away a graph from the graph is not a very good idea. You might get stuck in a maximal matching, and you end up throwing up some edges, some vertices. There's no
So
point of time we are throwing anything out.
Oh, no, so actually I meant it in the way that in the step of finding P1 through PT,
Right.
we can just start from an edge which is not in the matching,
Correct.
and then on both sides we just keep expanding until we see until we reach unsaturated vertices.
Yeah, basically that's the algorithm. Okay, but I mean, if you just think about it a bit more carefully, if you design it properly,
Okay.
and not design it properly, but design it meticulously rather, you will get that algorithm.
Okay.
Okay, but I want you go to think and do it. You're right, completely right. It's a traversal algorithm, and you traverse alternately between matched edges and non-matched edges.
And so we also have to prove why it will not have to run more than root feet number of times, right?
That will come second. Yeah, right. Yeah.
Or is it?
It is
obvious?
cheap. It is very easy. No, not obvious, but it is not hard.
Okay.
I don't want to do it right away because I want you guys to all think about it. First, design an algorithm to find an augmenting path in a matching.
Okay, sir.
Okay, and then try to use it to find disjoint matching.
Yes.
Okay, so I think I will not be going too far today. I want to kind of don't really want to really give too much stuff. I really request you guys to go back and think about this problem. Okay, both these problems, how to do the matching problem. Okay, how can you find an augmenting path? They're easy stuffs. I mean, forget the square root v, but just the how to find an augmenting path. Please go and think, and this reduction. So I have also given it for the non-bipartite setting. By the way, this second algorithm that I kind of explained, using this technique through the augmenting path, you realize I did not use bipartiteness at all. This algorithm goes through for general graphs.
Yes.
Yes, sir.
So, okay. Also, there is this. You have a assignment to be submitted, right? Sometime in that was due date was sometime this week, but
Sunday. Sunday.
Yeah, but I heard but some of you have requested me to kind of postpone it the due date, which is fine with me. So if you want to submit it by say even next Saturday or something like that, that's also okay with me. Also, did you guys hear from the dean's office? Hello. Yeah.
No, sir.
No.
So regarding what?
Regarding our exams and all. So I mean, so there is a
Yeah.
sudden change because of the Omicron variant and all. And as far as I know, right now, the dean's office is saying that the NSEM will be completely online.
Yes, sir. One of our batchmate mailed Dean, and we got a reply that we are going to have an online exam.
Yeah, so that's what I think this some of the people in the related to the hostels and people who are associated with some hospitals and all here, they did not want to take that risk, which is understandable to some time. So yeah, so our mid NSEM will be almost in the same way that we have had our mid-sem. Okay. So after today's class, there will be 2 more weeks of. There are 2 more weeks of stuff, right? Classes. So I will be only teaching for 1 more week. The last week, I don't want to really do anything that is part of this course. Okay. So if you guys, I don't want to. I will possibly do things which are more fun from about advanced courses and all those things. So
We shall have the tutorial session, right?
yes. Or tomorrow tutorial session. Yes, tomorrow you will have the tutorial session.
It will be in offline mode.
It would be in no, tomorrow will be in online mode only because I will not be taking it. Okay. And yeah.
Sir,
Yeah.
sir, after the course, like formally, if you finish it,
Yeah.
like, can you have a small session, like the way forward from here? Let's say if someone is interested, so what can how to go about from like this point, like having a background in algorithm,
Yes.
and what are the paths and like what are the resources that we can utilize?
I can talk about it in the NSEM. In the
yes,
end
sir.
last week I can talk about it.
Maybe even after the NSEMs works, like
See, I mean, I am available after NSEM. Whoever comes to me, I will give you the advice. I don't want to take a class or something like that.
okay, sir.
Okay, but if you guys are interested, I can even spend one class or some part of the class in the last week to talk about it. I mean, in short, your next thing to do would be in the next semester. You have these advanced algorithms, right? I mean,
Yes, sir.
although it has not yet been fixed who is teaching it, I will not be teaching it because I don't believe that one teacher should teach multiple courses, because you should see other teachers' perspective of these various courses and all. But hopefully, a very good teacher will be teaching it, and that is the first step of it. And yeah, we can have a talk on other courses and all that can come up that you guys can take, and otherwise how can you read other materials and stuff, things like that.
Thank you, sir.
Thank you, sir.
Sure. Okay, so I will stop today. And
Thank you, sir.
Thank you.
Thank you, sir.